Hey there, my name is Daniel, and welcome to Soothing Science. Here we explore science slowly, without rushing, without pressure, and allow complex ideas to unfold at their own pace. If you find comfort in slow, thoughtful explorations of science, you might consider subscribing and spending more time here. For now, get comfortable, and let's begin. When we look up at the night sky, we see stars scattered across the darkness. And if we think about it for a moment, we might wonder, how far does all of that go? Does it stop somewhere? Does space have an edge? The question seems simple enough. We're used to things having boundaries. A room has walls. A country has borders. Even the Earth itself is a sphere with a surface, a clear dividing line between planet and not planet. So it feels natural to assume that space too must either go on forever or stop somewhere. But here's where the simplicity ends, because when we actually try to think through what either of those options would mean, we run into problems. If space has an edge, what's on the other side of it? And if space goes on forever, how can something have no end? Both answers seem impossible in their own way. This isn't a failure of imagination. It's a signal that we're asking a question that cuts deeper than it first appeared. The structure of space itself, it turns out, doesn't have to follow the rules we've learned from living on the surface of a planet, moving through rooms and fields and cities. Tonight, we're going on this journey. We'll move slowly through what science has learned about the shape, the size, and the limits of space. We'll start with what we can see, then work our way outward through scales that become harder and harder to hold in mind. And we'll build, piece by piece, a framework for understanding what the universe might actually be. Let's begin with what we know from direct experience. On a clear night, far from city lights, we can see around 2,000 stars with our eyes alone. They appear as points of light, some brighter than others, scattered across a band of hazy glow we call the Milky Way. That glow is light from billions of stars, too distant and too faint to see individually, all blending together into a soft, luminous river across the sky. Every one of those visible stars is part of our galaxy. The Milky Way is a collection of several 100 billion stars, all held together by gravity, slowly rotating around a common center. Our Sun is one of those stars, located about 2/3 of the way out from the galactic center, in a relatively quiet arm of the spiral. The galaxy is large. If we traveled at the speed of light, the fastest speed anything can move, it would take us about 100,000 years to cross from one side of the Milky Way to the other. Light from the nearest star beyond our Sun, Proxima Centauri, takes over 4 years to reach us. Light from stars on the far side of the galaxy left those stars before human civilization began. Already we're dealing with distances that exceed human lifetimes, human history, even the span of our species. And we haven't yet left our own galaxy. Beyond the Milky Way, there are other galaxies. The nearest large galaxy to us is Andromeda, a spiral similar in size and structure to our own. Light from Andromeda takes about 2.5 million years to reach Earth. When we look at Andromeda through a telescope, we're seeing it as it was long before our ancestors walked upright, and Andromeda is close in cosmic terms. There are galaxies so far away that their light has been traveling toward us for billions of years, crossing distances so vast that the numbers stop meaning much in any intuitive sense. This is the observable universe, everything from which light has had time to reach us since the beginning. The edge of what we can see is not an edge of space itself, but an edge of time. There is certainly more universe beyond that boundary. We simply haven't been around long enough for its light to arrive. So the first thing to understand is that when we ask whether space ends, we're not asking about the limits of what we can see. the observable universe has a boundary, but that boundary is imposed by the history of light, not by the structure of space. The real question is whether space itself, the fabric in which all of this exists, has a limit. To approach this question, we need to think carefully about what we mean by space. In everyday life, space is the emptiness between things. It's the distance between here and there. It's what we move through. But space, as physics understands it, is not just an empty container. It's a thing in itself, with properties, with structure. It can bend. It can stretch. Under the right conditions, it can even carry waves, ripples that propagate outward like waves on a pond. This understanding comes from general relativity, the theory developed by Albert Einstein in the early 20th century. General relativity describes gravity not as a force that pulls objects toward each other, but as a curvature of space itself. Massive objects like stars and planets bend the space around them, and other objects move along the curved paths that result. We can visualize this roughly by imagining a heavy ball placed on a stretched rubber sheet. The ball creates a dip, a curvature in the sheet. If we roll a smaller ball nearby, it will curve toward the heavy ball, not because of any direct pull, but because it's following the curved surface. This analogy has limits. The rubber sheet is two-dimensional, and it's being bent in a third dimension that we can see from outside. But space itself is three-dimensional, and if it's curved, it's not curving into some external dimension we can point to. The curvature is intrinsic. It's a property of space itself, measurable from within. This is where the question of whether space ends becomes more precise. We're not asking whether there's a wall somewhere out in the universe. We're asking about the geometry of space on the largest scales. Is space flat, extending infinitely in all directions? Or is it curved in a way that makes it finite, even without an edge? There are three basic possibilities. The first is that space is flat. Flat space, in this context, means that the usual rules of Euclidean geometry apply everywhere. Parallel lines never meet. The angles of a triangle add up to 180 degrees. If space is flat and nothing else constrains it, it could extend infinitely in all directions. The second possibility is that space has positive curvature. This is analogous to the surface of a sphere. On a sphere, parallel lines eventually converge. The angles of a triangle add up to more than 180 degrees. And crucially, a sphere is finite in area, but it has no edge. If we walk in one direction on the surface of the Earth, we eventually come back to where we started, without ever hitting a boundary. If space has positive curvature, the universe could be finite in volume, but still have no edge. We could, in principle, travel in one direction through space and eventually return to our starting point, having circumnavigated the universe. The third possibility is that space has negative curvature. This is harder to visualize, but it's analogous to a saddle shape. In negatively curved space, parallel lines diverge. The angles of a triangle add up to less than 180 degrees. Negatively curved space can be infinite, extending forever without repeating. Each of these geometries is consistent with general relativity. The question of which one describes our universe is an empirical one. We have to measure it. How do we measure the curvature of space? We can't step outside the universe and look at it from a distance. We have to make measurements from within, using light and geometry. One of the most important tools for this is the cosmic microwave background, often abbreviated as the CMB. The CMB is a faint glow of radiation that fills the entire sky, coming from all directions. It's the leftover heat from the early universe, from a time about 380,000 years after the beginning, when the universe cooled enough for light to travel freely for the first time. Before that moment, the universe was so hot and dense that light couldn't move far without being absorbed and re-emitted by charged particles. The universe was opaque, like the interior of a thick fog. But as the universe expanded and cooled, a threshold was crossed. Electrons combined with nuclei to form the first neutral atoms, and light was released, streaming outward in all directions. That light has been traveling ever since. As the universe expanded, the light was stretched, shifting from visible wavelengths to microwaves. Today, it reaches us from every direction, carrying information about the state of the universe at that early time. The CMB is not perfectly uniform. There are tiny variations in temperature from one region of the sky to another. Fluctuations of only a few parts in 100,000. These variations are the imprints of density fluctuations in the early universe, slight differences in how much matter was concentrated in different regions. Over time, gravity amplified these differences, and they grew into the galaxies and galaxy clusters we see today. But for our purposes, what matters is the pattern of these fluctuations. The sizes and shapes of the hot and cold spots in the CMB depend on the geometry of space. If space is flat, the spots have a characteristic size that corresponds to a specific angle on the sky. If space is positively curved, the spots appear larger, because light rays traveling across a positively curved space converge slightly, magnifying distant images. If space is negatively curved, the spots appear smaller, because light rays diverge. By carefully mapping the CMB and measuring the sizes of these fluctuations, we can determine the curvature of space with remarkable precision. The result, from multiple independent observations over the past 2 decades, is clear. Space is flat, or at least very close to flat. The measurements are consistent with zero curvature to within about 1%. This tells us something profound. If space is flat, and if it extends uniformly in all directions, then it is very likely infinite. A finite, flat space is possible in principle, but it would require unusual boundary conditions, and there's no evidence for them. So the current best answer, based on what we can measure, is that space does not end. It goes on in all directions without limit. But this answer opens new questions. If space is infinite, then there is an infinite amount of space, filled with an infinite number of galaxies, stars, and planets. Everything that can happen, given enough space and enough time, will happen. Not just once, but infinitely many times. This is difficult to grasp, not because the math is complicated, but because our minds are not built to hold the concept of infinity in a concrete way. We can define it. We can work with it symbolically, but we can't picture it. Here's one way to approach it. The observable universe, the sphere of space from which light has had time to reach us, has a radius of about 46 billion light years. That's the distance to the edge of what we can see. Accounting for the expansion of space over the time the light has been traveling, within that sphere, there are roughly 2 trillion galaxies, each containing hundreds of billions of stars. The total number of stars in the observable universe is on the order of 10 to the power of 24. That's a 1 followed by 24 zeros. That number is enormous, but it's finite. We can write it down. We can imagine counting to it, in principle, even if it would take far longer than the age of the universe. But if space is infinite, then the observable universe is just a finite patch, one region among infinitely many. There are infinitely many other regions, each the size of our observable universe, scattered throughout space. And because the laws of physics are the same everywhere, those regions will, on average, look similar to ours. Same kinds of galaxies, same kinds of stars, same kinds of planets. In fact, if space is infinite and matter is distributed roughly uniformly, then every possible arrangement of matter that can occur within a finite volume will occur infinitely many times. There are infinitely many regions that look exactly like our observable universe, down to the smallest detail. There are infinitely many planets identical to Earth, with identical histories, where identical versions of ourselves are living identical lives. This is not speculation. It's a straightforward consequence of infinity combined with uniform randomness. If you have an infinite number of trials, and each trial has a finite number of possible outcomes, then every outcome occurs infinitely often. Most people find this disturbing, or at least strange. It seems to violate our sense of uniqueness, our feeling that our lives and our experiences are singular. But the strangeness comes from the concept of infinity itself, not from any failure of logic. And it raises a practical question. If there are infinitely many versions of us scattered across an infinite space, in what sense are we distinct? What makes this version here, the one we're experiencing right now, the one that matters? The answer has to do with locality. We can only interact with, observe, and influence the region of space that's close enough for light to have traveled within the history of the universe. Everything beyond that is, for all practical purposes, disconnected from us. Those distant regions exist, but they cannot affect us, and we cannot affect them. So while the universe may be infinite, the part of it that is relevant to us, the part we can touch and be touched by, is finite. This doesn't resolve the strangeness entirely, but it clarifies what we mean when we talk about our universe. We mean the observable universe, the local patch, the region of space with which we share a causal history. There's another complication. Space is not static, it's expanding. This expansion is not a movement of galaxies through space. It's an expansion of space itself. The distance between any two galaxies that are not bound together by gravity is increasing over time, not because the galaxies are moving, but because the space between them is stretching. This was first observed in the 1920s, when astronomers noticed that light from distant galaxies is shifted toward the red end of the spectrum. The farther the galaxy, the greater the redshift. This redshift is caused by the stretching of space. As light travels through expanding space, its wavelength is stretched along with it, shifting toward longer, redder wavelengths. The discovery of this expansion led to the realization that the universe had a beginning. If space is expanding now, it must have been smaller in the past. If we run the clock backward, space contracts, matter becomes denser and hotter, until we reach a point where the entire observable universe was compressed into an unimaginably small, hot, dense state. That moment, approximately 13.8 billion years ago, is what we call the Big Bang. It's not an explosion in space, but an expansion of space itself, from a state we cannot yet fully describe with our current physics. Since then, space has been expanding, and the expansion has consequences for what we can see. Because space is expanding, there are regions of space that are receding from us faster than light can travel through space. This doesn't violate the rule that nothing can move faster than light, because it's not a motion through space. It's the expansion of space itself. The result is that there are galaxies whose light will never reach us, no matter how long we wait. They are beyond what's called the cosmological horizon. Light they emit now is being carried away by the expansion of space faster than it can close the distance to us. These galaxies are part of the universe, but they are fundamentally inaccessible to us. And this horizon is not fixed. As the universe continues to expand, more and more galaxies will cross this threshold. Galaxies we can see now will eventually disappear from view, their light stretched and redshifted until it fades into nothing. In the very far future, Assuming the expansion continues, an observer in our galaxy would see only the local group of galaxies, the small cluster of which the Milky Way is a part. Everything else would have receded beyond the horizon. The universe would appear smaller, emptier, darker. This raises a subtle point. When we say the observable universe has a radius of 46 billion light-years, we're describing the distance to the farthest point from which light could have reached us by now. But that distance is not the same as the distance to the farthest point we will ever be able to see. Because of the expansion, some regions we can see now will eventually slip beyond our horizon. So even within an infinite universe, there is a boundary to what we can ever know. Not because space ends, but because the expansion of space limits how far light can travel before being carried away. This is a kind of edge, but it's an edge in time and causality, not an edge in space. The expansion of the universe is accelerating. This was discovered in the late 1990s, and it was a surprise. For most of the history of cosmology, the assumption was that the expansion would slow down over time because gravity pulls everything together. Even if the universe is expanding, the gravitational attraction between all the matter in it should act as a brake, slowing the expansion. But observations of distant supernovae, exploding stars that can be used as markers to measure cosmic distances, showed that the expansion is speeding up. Galaxies are moving apart faster now than they were in the past. Something is driving the expansion, working against gravity. We call this something dark energy, but the name is just a placeholder. We don't know what it is. The simplest explanation, and the one that fits the data best, is that empty space itself has energy. This is called the cosmological constant, or vacuum energy. Even in regions of space that contain no matter, no radiation, nothing at all, there is a small but non-zero amount of energy inherent in the fabric of space. This energy has an unusual property. Unlike matter or radiation, which dilute as space expands, the energy density of empty space remains constant. If you double the volume of a region, you double the amount of vacuum energy it contains. This means that as the universe expands and matter spreads out, becoming less dense, the relative importance of vacuum energy increases. And vacuum energy has a repulsive gravitational effect. It pushes space apart, causing the expansion to accelerate. This has profound implications for the future. If vacuum energy remains constant, the expansion will continue to accelerate forever. The universe will grow larger and larger, colder and emptier, with galaxies receding from each other at ever-increasing speeds. Eventually, the only things left within our cosmological horizon will be the stars and galaxies in our local group, bound together by gravity. Everything else will have disappeared from view. The observable universe will shrink, not because space is contracting, but because the expansion is carrying everything away. Trillions of years from now, the stars themselves will burn out. The universe will grow dark. The remaining matter will slowly decay or collapse into black holes. And even those black holes will eventually evaporate, radiating away their mass as faint Hawking radiation over timescales so long they dwarf the current age of the universe. In the end, if the expansion continues and vacuum energy dominates, the universe will approach a state of maximum entropy. A cold, dark, empty expanse with nothing left to change, nothing left to happen. This is sometimes called the heat death of the universe, but this is projecting far into the future, based on assumptions about physics that may not hold. We don't know whether vacuum energy is truly constant, or whether it might change over time. We don't know whether there are other forces or phenomena that might come into play on timescales we haven't yet considered. What we can say is that the universe we observe is expanding, and that expansion is accelerating. And if current trends continue, the future will be very different from the present. Let's step back and take stock of where we are. We started with a simple question. Does space ever end? And we found that the answer depends on what we mean by end. If we mean a physical edge, a wall beyond which there is nothing, then no, space does not end in that way. The geometry of space, as far as we can measure, is consistent with being infinite, extending in all directions without limit. If we mean a boundary to what we can observe, then yes, there is an edge to the observable universe, defined by the distance light can have traveled since the beginning. Beyond that edge, there is more space, but we cannot see it. If we mean a boundary to what we will ever be able to observe, even in principle, then yes, the accelerating expansion of space creates a cosmological horizon, beyond which events are forever inaccessible to us. And if we mean a limit to what we can know about the structure of space itself, then we are confronted with the limits of measurement and theory. We can measure the curvature of space within the observable universe, but we cannot directly test what happens on scales vastly larger than what we can see. So the question has multiple answers, each correct in its own context. But there's a deeper layer to this. Everything we've discussed so far assumes that space is a continuous, smooth fabric that we can describe with geometry and physics. But what if that assumption is wrong? What if space itself, on the smallest scales, has a structure we haven't yet uncovered? This brings us to the frontier of current physics, where general relativity meets quantum mechanics, and where our best theories begin to hint at limits to their own applicability. General relativity describes space as smooth and continuous, a fabric that can bend and stretch but has no fundamental graininess. Quantum mechanics, on the other hand, describes the world in terms of discrete, quantized units. Energy comes in packets called quanta. Matter is made of particles. Even properties like spin and charge come in specific, indivisible amounts. For most of the past century, these two theories have coexisted, each supremely successful in its own domain. General relativity works beautifully on large scales, describing the motion of planets, the bending of light around stars, the expansion of the universe. Quantum mechanics works beautifully on small scales, describing atoms, molecules, the interactions of particles. But they do not fit together. When we try to apply both theories to the same situation to describe the behavior of space and time on the smallest scales, the equations break down. We get infinities, nonsensical predictions, a signal that our theories are incomplete. The problem becomes acute when we consider black holes, regions where gravity is so strong that space is curved to an extreme degree, and quantum effects should be important. Or when we consider the very early universe, in the first fraction of a second after the Big Bang, when the entire observable universe was compressed into a volume smaller than an atom. In these regimes, we need a theory of quantum gravity, a framework that unifies general relativity and quantum mechanics into a single, consistent description. We don't yet have such a theory, but we have hints. And one of the most tantalizing hints is that space itself, on the smallest scales, might not be smooth at all. It might have a discrete structure, a kind of atomic graininess, below which the concept of distance and position loses meaning. This scale is called the Planck length, approximately 10 to the power of -35 meters. That's a decimal point followed by 34 zeros and then a 1. It's so small that if an atom were enlarged to the size of the observable universe, the Planck length would still be smaller than a human hair. At this scale, quantum fluctuations in the fabric of space become significant. Space itself might fluctuate, bubbling and frothing in ways that make the smooth geometry of general relativity just an approximation, a large-scale average over something far stranger. If space has a discrete structure at the Planck scale, then in some sense, space is made of something. There are fundamental units, building blocks from which space is constructed. And if that's true, then questions about the size and shape of space might have different answers depending on whether we're asking about the smooth, large-scale geometry or the underlying quantum structure. This is still speculative. We have no direct evidence for a quantum structure of space because we can't probe the Planck scale with any current or foreseeable technology. The energies required are far beyond what we can achieve in particle accelerators. The distances are far smaller than what we can resolve with any instrument. But the theoretical arguments are compelling. And if space does have a quantum structure, it would represent a fundamental limit to how we think about space itself. It would mean that space is not an infinite, continuous expanse, but something built from discrete pieces, perhaps finite in number, perhaps infinite but countable, like the integers rather than the real numbers. This doesn't answer the question of whether space ends, but it reframes it. Instead of asking whether space extends infinitely in a continuous way, we might ask whether there are infinitely many fundamental units of space, or whether the total number is finite. And that's a question we can't yet answer. There's another layer to consider, one that takes us even further from the familiar. If the universe underwent a period of extremely rapid expansion in its earliest moments, a process called inflation, then the observable universe might be just one small patch in a vastly larger structure. Inflation predicts that the expansion didn't stop everywhere at once. It stopped in some regions, like ours, creating pockets where galaxies and stars could form. But in other regions, inflation might still be going on, driving expansion at exponential rates, creating new pockets, new regions where inflation ends and matter condenses. This is the concept of eternal inflation. And it leads to the idea of a multiverse, a vast, possibly infinite collection of separate regions, each with its own local conditions, each effectively isolated from the others. In this picture, our observable universe is one bubble in an infinite foam. The other bubbles are out there, but we cannot see them because the space between them is expanding so fast that light cannot cross the gap. Each bubble might have different physical constants, different particles, different forces. The properties we observe in our universe, the mass of the electron, the strength of gravity, the speed of light, might be just local accidents, frozen in when our bubble formed. In other bubbles, the physics could be entirely different. This is deeply unsettling for many scientists, because it seems to undermine the possibility of a unique predictive theory of everything. If the constants of nature are just environmental variables, different in different bubbles, then we can't predict them from first principles. We can only observe what they happen to be in our region. But it's also a natural consequence of some of the most successful theories we have. Inflation solves several puzzles about the early universe, explaining why space is so flat, why the cosmic microwave background is so uniform, why the universe looks the same in all directions, and if inflation happened, eternal inflation is hard to avoid. So we're left with a scenario where space, in the sense of the total amount of it, might be vastly larger than the observable universe, perhaps infinite and divided into causally disconnected regions that we can never observe. Does space end? In this picture, our local patch of space, our bubble, might be finite. But the larger structure, the multiverse, could extend without limit. And we have no way to test this directly, because by definition, we cannot observe anything outside our bubble. This brings us to a fundamental epistemological question. What does it mean to ask whether something exists if we can never observe it, never interact with it, never test it? Some argue that questions about the multiverse are not scientific, because science is about making predictions that can be tested against observation. If a theory predicts things that are in principle unobservable, it falls outside the scope of science. Others argue that the multiverse is a prediction of theories that are testable in other ways. Inflation, for instance, makes predictions about the cosmic microwave background that have been confirmed. If inflation is correct, and if eternal inflation is a consequence, then the multiverse exists whether or not we can see it. This is a philosophical debate as much as a scientific one, and it doesn't have a clear resolution. But it highlights the fact that the question, does space ever end, pushes us to the edges of what we can know, and perhaps beyond. We've been talking about space, but we should also think about time. Because space and time are not separate. They're woven together into a single structure called space-time. General relativity treats time as a dimension, similar in some ways to the three dimensions of space. Events don't just happen at a location in space. They happen at a location in space-time, a specific point defined by both where and when. And just as we can ask whether space has an edge, we can ask whether time has a beginning or an end. The evidence suggests that time, or at least time as we know it, did have a beginning. The Big Bang was not just the start of the expansion of space, but the start of time itself. Before the Big Bang, there was no before because time didn't exist. This is hard to wrap our minds around because we're used to thinking of time as a river that flows, with a past that extends back indefinitely. But in the framework of general relativity, time is part of the structure of the universe, and that structure can have a boundary. At the moment of the Big Bang, space-time itself began. The question, what happened before, doesn't have an answer. Not because we don't know, but because the question doesn't make sense. It's like asking what's north of the North Pole. This doesn't mean that nothing existed before the Big Bang. It means that the concept of before breaks down. The laws of physics as we know them, the structure of space-time, the flow of time, all of that starts at the Big Bang. But this raises another question. If space-time had a beginning, does it have an end? The answer depends on the future of the universe. If the expansion continues to accelerate, driven by vacuum energy, then space-time will continue indefinitely into the future. The universe will grow colder, darker, emptier, but time will keep moving forward. If, on the other hand, the expansion someday reverses, if gravity eventually wins out and the universe starts to contract, then space-time could collapse back into a dense, hot state. A reverse Big Bang, sometimes called the Big Crunch. Time itself might end, or it might emerge into a new cycle, a new expansion. We don't know which scenario is correct because we don't know the ultimate fate of the universe. But the point is that time, like space, has structure. It's not an infinite, featureless backdrop. It's part of the physical universe, subject to the same laws and limitations. And when we ask whether space ends, we're implicitly asking about the structure of space-time, not just the structure of space alone. There's a broader question lurking beneath all of this. How much can we actually understand about the universe? We are biological creatures evolved on a small planet orbiting an ordinary star in an ordinary galaxy. Our brains evolved to navigate environments where space is measured in meters, time in seconds, energy in the effort required to lift a stone or run across a field. We did not evolve to think about distances of billions of light years, timescales of billions of years, the curvature of space, the quantization of energy. These are concepts we've built through abstraction, mathematics, careful observation, but they are far removed from the intuitive grasp we have of the world around us. So when we struggle to picture infinity, or to make sense of a universe that is both finite and without edges, or to understand what it means for time to begin, we're not just dealing with difficult ideas, we're pushing against the limits of what our minds were built to do. This doesn't mean we can't understand these things. We can. but our understanding is mediated by mathematics, by models, by analogies that only partially capture the reality. We can work with the equations, we can make predictions and test them, but we can't hold the full picture in our heads the way we can hold the image of a tree or a face. Some philosophers and scientists have argued that there might be aspects of reality that are simply beyond human comprehension, not because we lack the right tools or data, but because our cognitive architecture has inherent limits. Just as a dog cannot understand calculus, we might not be able to fully grasp certain features of the universe. This is a humbling thought, but it's also a realistic one. We've made extraordinary progress in understanding the cosmos, but there's no guarantee that every question has an answer we can comprehend. That said, we're not at that limit yet. The questions we're asking about the size and shape of space are difficult, but they're not impossible. We have theories, we have data, we have frameworks that make sense of what we observe, and we're still learning. The field of cosmology is young, only about a century old in its modern form. We've measured the expansion of the universe, mapped the cosmic microwave background, detected gravitational waves, observed the light from galaxies formed in the first few 100 million years after the Big Bang. Each new observation refines our understanding, confirms or challenges our theories, opens new questions. So while we may be limited in what we can ultimately know, we're nowhere near the end of what we can discover. Let's return once more to the original question. Does space ever end? We've explored what the question means, how we might answer it, what the evidence suggests, and we've seen that the answer is not a simple yes or no. Space, as far as we can measure, appears to be flat, which suggests it might be infinite. But even if it is, we can only ever observe a finite portion of it, limited by the speed of light and the age of the universe. Space is expanding, and that expansion is accelerating, which creates a horizon beyond which we can never see. Even in principle, this horizon is not an edge of space, but a limit of causality. Space might have a quantum structure on the smallest scales, a graininess at the Planck length, which would give it properties very different from the smooth continuum we experience. Space might be part of a larger multiverse, with our observable universe just one bubble in an infinite foam, each bubble isolated from the others by eternally inflating space between them. And finally, space is inseparable from time. When we ask about the structure of space, we're really asking about the structure of space-time. And that structure has a beginning, 13.8 billion years ago, and possibly a future that extends without end. So the question itself is rich with layers, and perhaps that's the most important thing to recognize. The universe is not obligated to conform to the categories our minds find comfortable. It is what it is. And our job is to observe it carefully, to build models that match what we see, and to remain open to the possibility that reality is stranger and more subtle than we imagine. To go deeper into what it means for space to have no edge, we need to spend time with geometry, not the geometry of triangles and circles drawn on paper, but the geometry of shapes and spaces that exist beyond our everyday experience. Consider again the surface of a sphere. If we lived on the surface of a perfectly smooth sphere, unable to perceive any third dimension, we would experience our world as flat. We could walk in any direction, measure distances, draw maps. As far as we could tell, space would extend in all directions without limit. But if we walked far enough in one direction, we would eventually return to our starting point. We could walk around the entire sphere, never encountering an edge, never finding a place where space stopped. The sphere is finite in area, but unbounded. This is what mathematicians call a closed geometry. It's finite but has no boundary. Now imagine the opposite. A saddle shape extending infinitely in all directions. This is a negatively curved space. If we lived on such a surface, we could walk forever in any direction and never return to where we started. Space would be infinite and unbounded in a different way. The flat geometry, the one that appears to describe our universe, is the boundary case between these two. A flat plane extends infinitely, and parallel lines remain parallel forever. It is infinite and unbounded. These geometries can be extended to 3 dimensions. A 3-dimensional space can be flat, positively curved, or negatively curved, just like a 2-dimensional surface. We can't visualize these curved 3-dimensional spaces directly, because we would need a 4th spatial dimension to see them from outside. But we can describe them mathematically, and we can measure their properties from within. The key insight is that the question of whether space ends is really a question about which geometry describes our universe. And that's a question we can answer, or at least constrain, to observation. The measurements we have, particularly from the cosmic microwave background, tell us that if space is curved, the curvature is very small. Space is flat to within about 1%. This means that on the scales we can observe, space looks flat. Whether it remains flat on much larger scales, far beyond what we can see, we cannot say. But the flatness we observe has implications. In standard cosmological models, a flat universe that began with the Big Bang and has been expanding ever since is likely to be infinite. There's no natural way to make it finite without introducing special boundary conditions that have no observational support, so the geometry points toward infinity. But infinity is not something we can prove. We can only say that the evidence is consistent with it, and that the alternatives require assumptions we have no reason to make. Underlying much of our understanding of the universe is an assumption called the cosmological principle. It states that the universe, when viewed on sufficiently large scales, is homogeneous and isotropic. Homogeneous means it looks the same at every location. Isotropic means it looks the same in every direction. This principle is both an assumption and an observation. It's an assumption in that we use it as a starting point for building models of the universe, but it's also supported by observation. When we look at the distribution of galaxies on the largest scales, we see a roughly uniform pattern. When we look at the cosmic microwave background, we see the same temperature, to within a few parts in 100,000 in every direction. The cosmological principle simplifies the equations of general relativity enormously. If the universe is the same everywhere and in every direction, then its evolution is determined by a few global parameters: the density of matter, the density of energy, the rate of expansion. But the principle also has limits. It applies only on very large scales, scales of hundreds of millions of light years or more. On smaller scales, the universe is clumpy. Matter is concentrated into galaxies, which are concentrated into clusters, which form filaments and voids in a vast cosmic web. And there's a deeper question. How do we know the cosmological principle holds beyond the observable universe? We can see that the universe looks uniform within the region we can observe. But what if, far beyond our horizon, the universe is different? What if there are regions where the density of matter is much higher or much lower? What if the constants of nature vary from place to place? We have no way to rule this out. The cosmological principle is a working assumption, justified by the fact that it leads to models that match what we observe, but it's not a proven fact. If the cosmological principle fails on scales larger than the observable universe, then our conclusions about the overall structure of space might be incomplete. The universe might have large-scale inhomogeneities, variations in density or curvature that affect its global geometry in ways we can't detect from our local perspective. This is another form of epistemic humility. We can measure and model the universe we see, but we must remain cautious about extrapolating too far beyond the reach of our observations. There's a line of reasoning that approaches the question of the universe's structure from a different angle. It asks, why is the universe the way it is? And more specifically, why is it suitable for the existence of observers like us? The constants of nature, the ones that determine the strength of gravity, the masses of particles, the expansion rate of the universe, all of these have values that fall within a narrow range that allows for the formation of stars, planets, and complex chemistry. If gravity were slightly stronger, stars would burn out too quickly for life to evolve. If it were slightly weaker, stars might never form at all. If the strong nuclear force were different, the elements necessary for life might not exist. This is sometimes called fine-tuning, and it raises a puzzle. Why should the constants have these particular values? One answer is that they just do. There's no deeper reason. The universe is what it is, and we happen to exist in it. Another answer invokes the multiverse. If there are many regions of space, or many separate universes, each with different constants, then it's not surprising that we find ourselves in one where the constants allow for life. We couldn't exist in the regions where stars don't form or where atoms are unstable. Our existence selects for a universe with the right properties. This is called the anthropic principle. In its weak form, it simply states that any observation we make must be compatible with our existence. We can only observe a universe capable of producing observers. In its strong form, it suggests that the existence of observers is somehow necessary, that the universe must have properties that allow for observers. The weak form is uncontroversial. It's a tautology. The strong form is more contentious because it seems to grant a special status to observers, as if the universe were designed for us. Most physicists prefer the multiverse interpretation. If the multiverse exists, and if different regions have different constants, then the anthropic principle becomes a selection effect, no different from asking why Earth has liquid water and breathable air. We're here because the conditions are right. Elsewhere, they're not. But this brings us back to the question of what lies beyond the observable universe. If the multiverse is real, then our local region, with its particular constants, is just one patch in a vastly larger structure. And the question of whether space ends becomes even more layered. Does our local patch of space end? Does the multiverse as a whole end? We don't know. And we may never know. But the anthropic perspective reminds us that our observations are limited not just by the reach of light, but by the fact that we can only observe a universe compatible with our existence. Most of the matter in the universe is invisible. We know it's there because of its gravitational effects, but it doesn't emit light or interact with light in any way we can detect. We call it dark matter. The evidence for dark matter comes from multiple sources. Galaxies rotate in a way that suggests they contain far more mass than we can see in stars and gas. Clusters of galaxies hold together with a gravitational strength that exceeds what the visible matter can provide. The cosmic microwave background contains patterns that require dark matter to have been present in the early universe. We don't know what dark matter is. It's not made of atoms. It's not any particle in the standard model of particle physics. It's something else. Something that interacts primarily through gravity. Dark matter makes up about 27% of the total mass energy of the universe. Ordinary matter, the stuff we're made of, the stuff stars and planets are made of, accounts for less than 5%. The rest, about 68%, is dark energy, the mysterious force driving the accelerated expansion. So when we talk about the universe, about space and matter and structure, we're mostly talking about things we can't see directly. We infer their existence from their effects, but we don't know their nature. This has implications for our understanding of whether space ends. If the universe contains vast amounts of matter we can't observe, then our picture of its large-scale structure is incomplete. Dark matter forms a kind of scaffolding on which galaxies and clusters form. It has a distribution, a pattern that extends across the observable universe and presumably beyond. But we can only map dark matter where it affects visible matter. We can't see it in the vast empty regions between galaxy clusters. We don't know if its distribution is truly uniform on the largest scales, or if there are variations we can't detect. And dark energy is even more mysterious. If it's truly the energy of empty space, then its density is fixed, and it will dominate the universe more and more as matter dilutes. But if it's something else, some field that varies over space or time, then its properties might be different in different regions. This uncertainty is humbling. We're trying to understand the structure of the entire universe, but we don't even know what most of it is made of. So far, we've been talking about space as three-dimensional. We move in three directions, up and down, left and right, forward and backward. These three dimensions, plus time, make up the four-dimensional space-time of general relativity. But some theories in physics suggest that there might be additional dimensions of space, dimensions we don't perceive because they're curled up, compactified into shapes so small that we can't detect them. This idea comes from string theory, a framework that attempts to unify general relativity and quantum mechanics by proposing that the fundamental constituents of nature are not point particles, but tiny vibrating loops of energy called strings. String theory requires extra dimensions to be mathematically consistent. The most common version requires 10 dimensions of space-time, 9 of space, and 1 of time. If these extra dimensions exist, why don't we see them? The answer is that they might be compactified, rolled up into tiny shapes at every point in the three-dimensional space we experience. Imagine an ant walking on a tightrope. From far away, the rope looks one-dimensional, a line, but up close, the ant can see that the rope has thickness, that it's really a cylinder with a second dimension curled around the first. In the same way, every point in our three-dimensional space might have extra dimensions curled up so small that we can't detect them. These dimensions could be on the order of the Planck length, or they could be slightly larger. If they're larger, we might be able to detect their effects in particle colliders or through their influence on gravity. If extra dimensions exist, they would change our picture of the universe in fundamental ways. Space would not be just the three-dimensional expanse we see, but a higher dimensional structure with a complex geometry. The question of whether space ends would become even more subtle, because we would need to ask about the structure of all the dimensions, not just the three we experience. Some versions of string theory also predict the landscape of possible universes, each corresponding to a different way the extra dimensions can be compactified. This landscape might contain an enormous number of possibilities, perhaps 10 to the power of 500 or more. If all of these possibilities are realized somewhere in a multiverse, then the diversity of physical laws and constants could be staggering. This is speculative. String theory has not yet made predictions that we can test directly, and it remains a work in progress, but it represents one of the most ambitious attempts to go beyond our current understanding of space and time, to find a deeper framework that explains why the universe has the structure it does. At the center of a black hole, general relativity predicts a singularity, a point where the curvature of space-time becomes infinite and the equations break down. At this singularity, our understanding of space and time fails. Similarly, at the moment of the Big Bang, the equations of general relativity point to a singularity, a point where the entire universe was compressed into a region of zero size and infinite density. These singularities are places where the theory stops working. They're not physical objects or events. They're signals that we've reached the limits of the theory, that we need a new framework to describe what happens. This is where quantum gravity becomes essential. A theory of quantum gravity would, presumably, resolve these singularities, replacing them with some kind of quantum structure that doesn't involve infinities. Some approaches to quantum gravity, like loop quantum gravity, suggest that space-time itself is quantized, made of discrete units. In this picture, there is no singularity at the center of a black hole, and no singularity at the Big Bang. Instead, there's a minimum scale, a smallest possible volume, below which the concept of space doesn't apply. If this is correct, then the question of whether space ends takes on a new meaning. Space would not be continuous, not an infinite expanse of points, but a network of discrete units, finite in size and number, at least within any finite region. But even in this picture, the total number of these units could be infinite if space extends infinitely, so the question doesn't go away. It just shifts to a different level. Other approaches, like string theory, suggest that space-time emerges from something more fundamental, a web of quantum entanglement or a holographic boundary. In these frameworks, space and time are not the basic building blocks of reality, but emergent phenomena, patterns that arise from deeper structures. If space-time is emergent, then asking whether space ends is like asking whether the image on a computer screen ends. The screen has boundaries, but the information that generates the image might not. The question shifts from the nature of space itself to the nature of the underlying substrate. These are frontier ideas, far from settled science, but they illustrate how deeply the question of space's structure cuts into our understanding of reality. It's not just a question about geometry or cosmology. It's a question about the fundamental nature of existence. Let's step back from the theoretical frontiers and think about scale in a more human way. What does it mean, practically, that the universe is so large? If space is infinite, or even if it's just vastly larger than the observable universe, then most of reality is completely irrelevant to us. We will never interact with it. It will never affect our lives, our planet, our galaxy, or even our local supercluster of galaxies. The observable universe is already unimaginably large, but it's the only part that matters to us in any practical sense. Everything beyond the cosmological horizon might as well not exist, from our perspective. This raises a question about the nature of existence itself. Does something exist if it can never, even in principle, affect us? This is a philosophical question, not a scientific one, but it's worth considering. Most physicists would say yes, things exist independently of our ability to observe them. The far side of the moon existed before anyone saw it. Galaxies beyond our horizon exist even though we can't see them. Existence is not contingent on observation. But there's a subtlety here. In quantum mechanics, the act of observation plays a role in determining the state of a system. Before a measurement is made, a quantum system exists in a superposition of possible states. The measurement collapses the superposition into a definite outcome. This has led some to question whether reality is observer-dependent, whether things only exist when they're observed. Most interpretations of quantum mechanics reject this extreme view, but the question remains open, debated among philosophers and physicists. For our purposes, the relevant point is that the universe is vastly larger than the part we can interact with. Whether the rest exists in some absolute sense or not, it doesn't affect our lives. We are confined to a small bubble, a finite region of space-time, and that's where our story unfolds. In a sense, this is reassuring. We don't need to understand the entire universe to understand our place in it. We can focus on the observable, the accessible, the part of reality we can touch and be touched by. But in another sense, it's humbling. We are part of something so much larger than ourselves, so much larger than we can ever fully grasp. And the question of whether space ends is a reminder of that scale, a prompt to think about our existence in the largest possible context. Infinity is not just a mathematical concept. It's an idea that carries psychological weight. When we try to imagine something going on forever, without end, we feel a kind of vertigo, a sense of the ground falling away beneath us. This is not surprising. Our minds evolved to deal with finite things, finite resources, finite distances, finite lifetimes. We can plan for the future because the future is finite. We can understand our environment because it's finite. The concept of infinity is alien to our everyday experience. But the universe doesn't care about our psychological comfort. If space is infinite, then it is, regardless of how that makes us feel. One way to cope with infinity is to recognize that we don't need to hold it in our minds all at once. We can work with it in pieces, through abstraction and mathematics. We can understand its properties without visualizing it. Another way is to focus on the finite within the infinite. Even if space is infinite, our lives are finite. Our experiences are finite. The part of the universe we care about is finite. Infinity is a backdrop, a context, but it's not where we live. And yet, there's something profound about the idea that the universe might be infinite. It suggests that reality is richer, vaster, more complex than we can ever fully know. It suggests that no matter how much we learn, there will always be more to discover. In some spiritual or philosophical traditions, infinity is associated with the divine, with the eternal, with the ultimate. The infinite universe becomes a symbol of transcendence, of something beyond human limits. Science doesn't deal in symbols or transcendence, but it does reveal the universe as it is. And that revelation can inspire awe just as effectively as any religious vision. The knowledge that we live in a universe without edges, without limits, in a cosmos that stretches beyond comprehension, is a kind of secular sublime. Our understanding of the universe is not static. It's evolving, refining, deepening as new observations come in and new theories are developed. In the coming decades, we'll launch new telescopes, build new detectors, probe the universe with instruments more sensitive than anything we have now. We'll map the cosmic microwave background with greater precision, search for gravitational waves from the earliest moments of the universe, observe the first stars and galaxies with unprecedented clarity. Each new observation will refine our understanding of the universe's geometry, its composition, its history. We'll constrain the curvature of space more tightly, test the predictions of inflation, search for signs of extra dimensions or quantum structure. We may not find definitive answers to the question of whether space ends. Some questions might remain beyond the reach of observation, limited by the horizon of the observable universe or the constraints of causality. But we'll learn more. We always do. The history of cosmology is a history of surprises, of observations that challenged assumptions, of theories that opened new possibilities. A century ago, we didn't know the universe was expanding. We didn't know about the Big Bang, the cosmic microwave background, dark matter, dark energy. We didn't know that galaxies existed beyond our own. The entire modern picture of cosmology has been built in a single human lifetime. It's reasonable to expect that the next century will bring discoveries just as surprising, just as transformative. We may find evidence for the multiverse or rule it out. We may develop a theory of quantum gravity that resolves the singularities and explains the structure of space on the smallest scales. We may discover new forces, new particles, new dimensions, hope we may find that the universe is simpler than we thought, that the questions we've been asking were based on misconceptions, that the answers lie in a framework we haven't yet imagined. Science is a process, not a destination. The question of whether space ends is part of that process, a question that drives us to observe more carefully, to think more clearly, to build better theories. For most of human history, the stars seemed eternal and unchanging. The constellations our ancestors saw are the same we see today. The patterns in the sky have been stable for thousands of years, a fixed backdrop to the shifting drama of human affairs. But we now know that this is an illusion of time-scale. Stars are born, they live, they die. Galaxies collide and merge. The universe is dynamic, evolving, changing on timescales so long that human history is a blink. The expansion of space is one of these slow, vast processes. On human timescales, it's imperceptible. The distance between galaxies increases, but so slowly that we can only detect it through careful measurement of light from distant sources. Yet this slow expansion has profound implications. It means the universe has a history, a direction of change. It means that the future will be different from the present, and the present is different from the past. In the far future, if the expansion continues, the universe will be a very different place. Galaxies will be isolated, separated by vast empty spaces. The cosmic microwave background will fade, red-shifted into invisibility. Stars will burn out, and new stars will stop forming as gas is exhausted. Eventually, even the largest structures will decay. Galaxies will evaporate as stars are flung out into the void. Black holes will form and then slowly evaporate through Hawking radiation. The universe will approach a state of maximum entropy, a cold equilibrium with nothing left to change. This is the heat death, the ultimate fate of a universe dominated by dark energy. It's not a dramatic ending, not a collapse or an explosion, but a slow fading into emptiness. But this is trillions of years in the future, a time scale so long that it's hard to relate to. For now, the universe is vibrant, dynamic, full of stars and galaxies and structure, and we are here, in this moment, able to observe it and think about it and ask questions about its nature. There's something remarkable about the fact that we can ask whether space ends. We are arrangements of matter, complex but ultimately made of the same atoms as rocks and clouds and stars. Yet we can think about the structure of space itself. We can build theories and test them. We can measure the curvature of the universe and reason about infinity. This capacity for abstract thought, for science, for philosophy, is one of the most extraordinary features of the universe. As far as we know, we are the only place in the observable universe where matter has organized itself into something capable of asking these questions. That might not be true. There could be other civilizations out there, scattered among the billions of galaxies, asking the same questions, building their own telescopes, developing their own theories. We don't know. We haven't found any sign of them yet. But whether we're alone or not, the fact that we're here, that we can think and observe and wonder, is profound. We are the universe examining itself, matter becoming aware of matter, space contemplating space. This is not a mystical statement. It's a straightforward description of what we are. We are part of the universe, and we are capable of understanding it, at least in part. And the questions we ask, like whether space ends, are not idle curiosities. They're part of a larger effort to understand where we are, what we are, how we fit into the larger whole. We may never have complete answers, The universe is vast and we are small. Our instruments have limits, our theories are provisional. Our observations are constrained by the horizon of the observable and the reach of causality. But we keep asking, we keep looking, we keep building better tools and better models. And in the process, we learn not just about the universe, but about ourselves, about what it means to be a thinking thing in a cosmos that is larger and stranger than we ever imagined. So, does space ever end? We've traveled through scales from the observable universe to the quantum structure of space-time itself. We've considered flat geometries and curved ones, finite volumes and infinite expanses. We've looked at the expansion of space, the horizon of observation, the multiverse, the limits of theory, and the answer we arrive at is not a simple yes or no, but a recognition that the question touches on multiple layers of reality, each with its own kind of boundary or lack thereof. The space we can see has a boundary defined by time and light. Beyond that boundary, there is more space, but we cannot observe it. The space we can ever hope to interact with has a boundary defined by the accelerating expansion. Beyond the cosmological horizon, there are regions of space that are fundamentally inaccessible to us. The geometry of space itself, as far as we can measure, is consistent with being flat and infinite. There is no edge, no wall, no place where space stops. It extends as far as we can tell without limit. But this infinity is not something we can prove. It's an extrapolation from what we observe within the finite region accessible to us. The universe beyond our horizon could be different. Space could be curved on scales too large for us to detect. It could be part of a multiverse, one bubble among many. It could have a quantum structure that makes the very concept of continuous space an approximation. We don't know these things. We may never know them, but we have a framework for thinking about them, a way of turning vague questions into precise ones that can be addressed with observation and theory. And that framework tells us that the universe is not a simple container with walls. It's not a room with corners or a sphere with a surface. It's a dynamic, four-dimensional structure, woven from space and time, shaped by matter and energy, evolving according to laws we can write down and test. Within this framework, the question of whether space ends becomes a question about geometry, about curvature, about the global topology of space-time. And the answer, tentative but supported by evidence, is that space very likely does not end in any simple sense. It may be infinite. It may be part of something larger that we cannot see. It may have a structure on the smallest scales that we cannot yet describe. But it does not have an edge. This is the current state of our knowledge. It's not the final word, because science is never final, but it's where we are, after a century of careful observation and deep thought. When we look up at the night sky, most of what we see is darkness. The stars are scattered points of light, but the space between them is black. That darkness is not empty. It's filled with photons from distant galaxies, neutrinos from the sun, cosmic rays from supernovae, the faint glow of the cosmic microwave background. It's filled with dark matter, invisible but present, threading through everything. But to our eyes, it looks empty. And in that darkness, we can project our questions, our uncertainties, our sense of the vastness of it all. The darkness between stars is the space we've been talking about. It's the fabric of the universe, the stage on which everything plays out, and it goes on. Farther than we can see, farther than we can imagine, without apparent end. Some find this thought disturbing. a reminder of insignificance, of the smallness of human concerns against the scale of the cosmos. Others find it liberating, a sense that we are part of something larger, something that transcends the boundaries of individual life and human history. Both responses are valid. The universe is indifferent to our feelings about it. It simply is, but how we respond to that fact, how we integrate it into our understanding of ourselves, is up to us. For those who spend their lives studying the universe, the vastness is not a source of despair, but of wonder. Each new observation, each new measurement, each new theory opens a window into something larger, reveals a pattern or structure that was hidden before. The question of whether space ends is part of that wonder. It's a question that leads us outward, away from the familiar, into the unknown, and in following it, we learn not just about space, but about the nature of reality itself. If we could stand outside the flow of time, if we could watch the universe from its beginning to its end, we would see a story unfold in silence. At first, the rapid expansion, the cooling, the formation of the first atoms, the first light, then a long period of darkness, hundreds of millions of years as gravity slowly pulled matter together into clumps. The ignition of the first stars, the formation of the first galaxies, the universe lighting up, filling with structure. Billions of years of slow evolution, galaxies merging, stars forming and dying, heavy elements being forged in supernovae and scattered into space, planets forming around new stars. The emergence of complexity, chemistry, perhaps life, and then, in the far future, the slow decline. Stars burning out, galaxies fading, the expansion accelerating, everything receding from everything else. The universe growing colder, darker, emptier, until only the faintest remnants remain. And finally, silence. No more stars, no more light, no more change. Just space, expanding, empty, approaching a state of equilibrium that will last forever. This is the trajectory we're on, if current trends continue. It's not a happy ending, but it's not a sad one either. It's just what happens in a universe governed by the laws of physics, where entropy increases and energy spreads out and everything moves toward equilibrium. But this endpoint is so far in the future that it's almost abstract. For now, for the next trillion years at least, the universe is alive with light and motion and change. Stars are still forming, galaxies are still evolving, and somewhere, perhaps in many places, conscious beings are looking up at the sky and asking questions. We are here in the brief window when the universe is comprehensible, when there's enough structure to observe and enough time to think. We're fortunate to exist in this moment, in this place, able to participate in the grand project of understanding. In asking whether space ends, we're also asking about the edges of our own understanding. Where does knowledge stop? What lies beyond the boundary of what we can know? These are not just questions about the universe, they're questions about us, about the limits of human cognition, about what it means to understand something. We've built a remarkable edifice of knowledge over the past few centuries. We've mapped the Earth, charted the stars, decoded the atom, sequenced the genome. We've developed theories that predict the motion of planets, the structure of molecules, the evolution of species, the expansion of space. But each answer raises new questions. Each boundary we push back reveals another boundary beyond it. This is the nature of science. It's not a process of finding final answers, but of refining questions, of building better and better approximations to the truth. The question of whether space ends is one of those questions that pushes us to the edge. It forces us to think about the largest scales, the most fundamental structures. It tests the limits of our theories and our observations. And in some ways, the fact that we can't answer it definitively is part of what makes it interesting. It reminds us that the universe is not obligated to be simple or transparent. There are mysteries, depths, layers of complexity that we're still uncovering. But we're not helpless in the face of these mysteries. We have tools, methods, frameworks for making progress. We can measure, we can calculate, we can test. And slowly, incrementally, we learn. The edges of our understanding are not walls, they're horizons, and horizons can be approached even if they recede as we move toward them. Let's take stock one more time of what we actually know as opposed to what we speculate or wonder about. We know that the universe is expanding. This is measured, confirmed by multiple independent observations. The expansion is real. We know that the universe has a history, that it was denser and hotter in the past, that it began in a state we call the Big Bang approximately 13.8 billion years ago. This is supported by the cosmic microwave background, the abundance of light elements, the distribution of galaxies. We know that space is very close to flat on the scales we can measure. This comes from precise observations of the cosmic microwave background and the large-scale structure of the universe. We know that most of the universe is made of dark matter and dark energy, substances we don't yet understand, but whose effects we can observe. These are facts, as solid as scientific facts can be. They're supported by decades of observation and fit into a consistent framework that makes predictions we can test. Beyond these facts, we have well-supported theories. General relativity describes gravity and the curvature of space. The standard model of cosmology, the lambda CDM model, describes the evolution and structure of the universe. These theories work. They match what we see. And then we have speculations, ideas that are plausible, that fit within our theoretical frameworks, but that we can't yet test. The idea that space is infinite. The idea that there's a multiverse. The idea that space has a quantum structure at the Planck scale. These speculations are not wild guesses. They're motivated by theory, by the logical extension of ideas that have proven successful, but they're not yet established facts. The boundary between what we know and what we wonder is not sharp. Science advances by turning speculations into testable predictions, by finding ways to observe what was previously unobservable. The question of whether space ends sits right on this boundary. We have theoretical reasons to think it probably doesn't, but we can't observe the entire universe to confirm it. We're limited by the speed of light, the age of the universe, the horizon of observation. And that's okay. Science doesn't require certainty. It requires honesty about what we know and what we don't. A willingness to follow the evidence and the patience to live with uncertainty while we work to reduce it. In the end, the universe we inhabit is the observable universe. That's the only universe we can interact with, the only one that's relevant to our existence. And that universe is large enough, complex enough, beautiful enough to occupy us for lifetimes. There are billions of galaxies to study, trillions of stars, uncounted planets. There are phenomena we've barely begun to understand. Black holes, neutron stars, gamma ray bursts, gravitational waves. There is the entire history of the universe to reconstruct. From the first moments after the Big Bang, to the formation of the first stars, to the emergence of galaxies and clusters and the cosmic web, there's the chemistry of life, the evolution of complexity, the question of whether we're alone or whether consciousness has emerged elsewhere among the stars. All of this is within the observable universe, within reach of our telescopes and our theories. Whether space extends infinitely beyond what we can see, whether there are other bubbles in a multiverse, whether space has a quantum structure we can't yet probe. These are fascinating questions, but they don't diminish the richness of what we can study. We live in a universe that is knowable, at least in part. We can observe it, measure it, understand it. We can trace the paths of planets, decode the spectra of distant stars, map the fluctuations in the cosmic microwave background. And in doing so, we find our place. We're not at the center, not special in any cosmic sense. We're one planet among billions, in one galaxy among trillions, in one small patch of impossibly infinite space. But we're here. We're aware. We can think and wonder and explore. And that in itself is extraordinary. The universe may not care that we exist, but we care. We care about understanding it, about finding our place within it, about passing that understanding on to those who come after us. And so we keep asking questions. Does space ever end? What is the universe made of? Where did it come from? Where is it going? These questions have driven us to build observatories and particle accelerators, to develop theories of quantum mechanics and relativity, to send spacecraft to the edges of the solar system and peer through telescopes at galaxies billions of light years away. They've driven us to think carefully about what we mean by space and time, about the nature of existence, about the limits of knowledge. And they've connected us to something larger than ourselves, to the grand project of understanding that stretches back through history and forward into the future. On a clear night, far from city lights, the Milky Way stretches across the sky like a river of faint light. Each point in that glow is a sun, or hundreds of suns, or millions, too far away to see individually, but present nonetheless. And beyond the Milky Way, in the darkness between the stars, there are other galaxies, invisible to the naked eye. But there, billions of them, each containing billions of stars, and all of it, all the light and darkness, all the matter and energy, exists within space, the three-dimensional expanse that extends in all directions from where we stand. Does that space have an end? Probably not. The evidence suggests that it goes on without limit, without boundary, as far as we can tell. But even if there were some edge, far beyond what we can see, it wouldn't change what we observe here, in our small corner of the cosmos. We are embedded in this vast structure, part of it, made from it. The atoms in our bodies were forged in stars that lived and died before the sun was born. The space through which we move is the same space that stretches to the most distant galaxies and beyond. We are not separate from the universe. We are expressions of it, patterns of matter and energy that have become complex enough to be aware, to ask questions, to seek understanding. And in this moment, on this planet, in this galaxy, we can look out at the stars and think about infinity. We can wonder about the structure of space, the curvature of the universe, the nature of time. We can ask whether space ends, and even if we can't answer with certainty, we can explore the question, follow it where it leads, learn what we can. This is what it means to be human in the 21st century. We have inherited the accumulated knowledge of countless generations, the observations and theories and insights that have been built up over centuries, and we have the tools and the understanding to push further, to ask deeper questions, to see farther than anyone before us. The universe is vast. Space may be infinite. But we are here, in this moment, able to contemplate it all. And that, perhaps, is answer enough.